Having this result in hand, we can give you examples of what? Of continuous vector valued functions. Okay. We previously had an example of a continuous function f equal to sine square root of x squared plus y squared, which is a two variable, one dependent variable continuous function. Now we want to study a higher dimensional case. Suppose A is n by n matrix. Aij belongs to R, and the function f is given by this Rn to Rn, defined on Rn, taken value in Rn. Fx is Ax. Here we write the independent variable x by a column vector x1, xn, so that it will be convenient to take metric multiplication. This is not essential to denote x by a row vector or column vector. This is not essential. So for convenience, for this example, we use column vectors. Okay. So we declare that f is continuous. So Ax, what's Ax? Ax is A11, An1, Am1, Amn, X1, Xn. Okay, this is our function f. Function from Rn to Rm. We said that this is continuous. F is continuous. How to prove this? How to prove this result? Of course, we can only use the definition. Okay, but maybe it will be convenient to consider the component functions of f. Fx is by metric multiplication. It will also be convenient to write the components of to write fx in a column vector. So the component of fx is f1x, fmx. So you see the component, the i's component of fx is what? Is fix, which is the sum of I from 1 to n, j from 1 to n, xj. By metric multiplication, we see that fix is this sum. So we want to show that f is continuous. By the previous theorem, it's sufficient to show that all the component function fi is continuous. So to prove that fi is continuous, we take xk be a sequence in Rn, and xk converts to the point A. Continue, we take a point A. Whether fi is continuous at this point, at the point A. So this is our question. For this reason, for this purpose, we consider xk in Rn. Xk converts to the point A. We might write xk to be. Oh, I have no place to write this. Xk1, xkn. because xk is a point in Rn, it has n components. So our Fixk, what's this? This is sigma j from 1 to n aij xjk. Not very clear. I write clearer, more clear. Right? Simply replace the xj by xjk because x is a sequence xk. Okay. Now this xkj convert to the component of aj. So by the property of a conversion sequence of real numbers, this will converge to the sum of aij aj, which is exactly Fia. Sorry, we have not enough place to write this down. Anyway, the idea is clear, or I will write it in the next page. Sorry. So Fixk is J1 aij xjk. Here, note that xk is xk1 xkn. So we have this. Fi is this sum, but because xk converge to a is a1 an, therefore every xjk converge to aj. So this sum will converge to the aij, which is exactly Fia. So Fi is continuous. Therefore, F is also continuous at this point A. And A is an arbitrary point in Rn, so F is a continuous function from Rn to Rm. Okay? Okay, we have introduced the concept of continuous functions, and now we want to construct new continuous functions from old ones. Okay, this is the continuity under common operations. Continuity under operations. This is the theorem. If F and G are defined on A to Rm, if both F and G are continuous at the point small a, of course, belongs to the domain of definition, and the lambda and the mu are real numbers. Okay, then what conclusion can we obtain? Then lambda f plus mu g and f dot g. Here we use the dot notation to denote the scalar product or inner product. So these two functions are also continuous. At the point A. Okay, so we can obtain new continuous functions from f and g. I will remind you that lambda f plus mu g is the linear combination of two functions. They are vector valued functions because both f and g take value in Rn. Therefore, lambda f plus mu g is a function defined on Rn taking value in Rn. The value of this function, how this function defined? This function is defined in this way. For any independent variable x, the value of this function at this point x is lambda fx plus mu gx. Here fx and gx are points in Rn. Therefore, lambda fx is the scalar multiplication. Mu gx is also scalar multiplication. Then this is the sum addition in Rn. So this makes sense. Well, f dot g is also a new function defined on Rn, but where this function takes its value is a real valued function. F dot g x is the scalar product of fx and gx. Both fx and gx are elements of Rn. So this is a scalar product in Rn. So I explained to you that these two functions involved in the statement of this result. I explained it to you here. Okay. Now we'll prove this result.